a sound of like, and then the board, right?
Yep, sound in the board when it records. So you're good. All right, guys, grab your note sheet. I would put this at the very top. Let's title this. These are your periodic trends. Yes? Yeah. Coming up. Okay, so we're talking periodic trends today. We're going to take the activity we did last time, thank you, where we graphed out the relationship between atomic radius and electronegativity. We're going to make sense of that today. And then we're going to get building blocks for understanding the rest of the unit, which is all about how things bond together. That's where this starts to get really cool, okay? Because you're going to be able to start to make predictions about how things bond together. When we understand how they bond and we understand the shapes that they make, that helps us understand the world around us, which is pretty sweet. And then when you choose to come on and take AP in the future, they take that even further to the next level, and it's so interesting. It's very cool. Strongly recommend AP. And if you're considering anything in the future that might even require science, you're going to want to take chemistry, okay? They call chemistry the central science because it connects to pretty much anything. So if you're considering the medical field, any sort of engineering, you're going to want chem. All right, let's do this thing. Very first thing we need is just some vocab. Some vocab so we're on the same page about how we talk. You see in the top, is it top right? Yep, top right corner of your notes here, you've got kind of a mini periodic table, and I've got my periodic table right here. We're going to talk about a couple of vocab words that we can use to talk about the periodic table and where things are. The first thing are periods. Periods are the horizontal rows on our periodic table. So those are the ones that go across like this, right? Horizontal rows this way. Okay. How many are there? There are 7, right? We already knew that because the periods also represent what? Energy. Our energy levels, right? So our energy levels are our periods, okay? That's why there's 7 of them. And as we go down, we're adding on layers, right? Layers each time. So our periods are our energy levels. Those are our horizontal rows. Okay. Our groups, on the other hand, are the vertical columns. Okay, that's these guys. This is a group, and this is a group, and this is a group. These are our groups right there. Okay, groups are pretty awesome because they all have the same number of valence electrons. Right? We knew that already. We know that here, how many valence electrons do they have right here? All of them have 1 valence electron. How many do they have here? 2. All of these all have how many? 2, right? How many do these have? 3. How many do these have? 4, right? 1, 2, 3, 4 valence electrons, and so on and so forth. And because they all have the same amount of valence electrons, they all react similarly, right? They react similarly. We've talked about how these guys react in this first row. Whoops. Not sky blue. Let's go blue, blue. In this first row, when these get dropped into water, what happens? Boom, right? They blow up, right? Yeah.
Why is hydrogen in that row? It doesn't seem to go with the rest of the period.
Why does hydrogen fit right in here?
Yeah, all the rest of the metals.
Right. So this one actually is a metal. Isn't that weird? Hydrogen's a metal. Okay, we're going to talk about why a little later today. I know, right? What? It's a metal, but because it's a gas, you're right, it doesn't explode when it touches water. It's also quite reactive. Yeah, metals can be gases. Yes, I know, right? So we're going to talk today about what we mean by metals, because what you hear by metals is limited, okay? And it's similar with the word organic. It kills me when everything's organic. I'm like, organic just means it contains carbon. There are a lot of things that are organic, okay? Yeah.
So if hydrogen was in its solid form, would it blow up on water?
Potentially it should. Yes, because it's also quite reactive, right? So each of these, right, we know lithium does. And then as we go down each of, what are those horizontal rows called again? Each of the groups, as we go down in these groups, they get more and more reactive. The explosion gets bigger and bigger and bigger and crazier. Okay? Good. All right, guys, we want to label these groups. Will you go ahead and number those groups? Group number 1, group number 2, number 3, 4, 5, 6, 7, and 8. We use these group numbers to reference how many valence electrons they have. Okay? So you can call it group 1, group 2, group 3, group 4, group 5, group 6, group 7, group 8. But they also have other names that we refer to them by. Like, for example, in this space right here, that's group 8, but we also know that they are called noble gases. These are our noble gases, okay? Why? Why do they call it noble gases? If you think about it, what's unique about how they react? Do they react?
They're noble.
No, they are noble. They don't react. They have 8 valence electrons. They're completely full. Because they're completely full, they're stable. They don't react with other things, okay? They are noble gases because they're like, all the other ones are peasants and stay away from me, okay? That's honestly how like that, because they're separated, they're noble, they're above all that reacting nonsense. Yeah. There we go, different kind of reaction, but yes. Okay, oh no! This could be an adventurous recording if my computer decides to do this all day. There we go. These ones over here, group number 1, are what are called the alkali metals. We're going to world language this, make sure you can pronounce it. Everyone, alkali. Alkali. Ah, super. So, yeah, okay. So alkali metals are our ones that are super reactive when they hit water. The ones right next to it are called our alkaline earth metals. Everybody, alkaline. Alkaline. Awesome, you guys have got this. Our alkaline earth metals. Have you heard the word alkaline before? Yeah? What context?
Usually people lying about water, but also just general chemistry stuff.
Right. So you hear it, like you said, kind of with water, and like environmental science sometimes stuff, because when they find alkaline materials, they're finding stuff that contains these elements in them. They're often referred to as well when you're talking about acids and bases, right? So you'll hear that. Okay, the next one we want are our transition metals. The whole D block, everything in the D orbitals, those are transition metals because they're kind of transitioning us from S to P. So those are transition metals, all right? Then the last one that we're going to talk about up here on this are halogens. Everybody, halogens. Halogens. Very good. And halogens have how many valence electrons? 7, right? So how many more do they need to be completely full? 1. They only need 1. They're so close, making them very reactive. Our halogens are very reactive as well. For example, most of them, like fluorine, chlorine, bromine, and iodine, they are so reactive that if you just have plain fluorine, it'll bond with itself. Okay? Chlorine, it'll bond with itself. Bromine will bond with itself. Iodine will bond with itself. They're so reactive that they can't stand to be alone. So they'll bond with themselves. Yep. Yes, it is. Both of these are highly poisonous. Yes. Yep. Crazy. Yeah, chlorine gas, that's mustard gas. Yeah. That's bad news. Okay, good. The last ones we want to label are these guys. These are our lanthanoids. Okay, everybody, lanthanoids. Lanthanoids. And actinoids. Actinoids. Does that sound like it comes straight out of science fiction? It's like a robot name, right? But it totally does, right? Totally does. So, and the names feel really random, but they're actually kind of logical, okay? So you see, our lanthanoids begin with element number 58, yes? Okay, look at the element that comes just before it. Look at number 57. What is it called? Lanthanum. So, they named these the lanthanoids because they come right after lanthanum. Right? And then look at our actinoids. If I look at, well, actinoids begin on number 90. Look at number 89. What's it called? Actinium. So they named these the actinoids because they come right after actinium. So, yay for logic, even though it sounds straight out of science fiction. Yeah?
So is both alkaline and alkali both very reactive, or is it just alkaline?
Yeah, they're both quite reactive. The alkali metals are more reactive, say, with water, right? These ones aren't quite as reactive with water, but they are quite reactive. They'll react pretty well. Alkali are reactive with water. Alkaline are not. The alkaline earth metals. Okay. All right, guys, that's the vocab that we need to better be able to discuss the trends we're gonna talk about today. Okay, so we're gonna talk through 4 trends. Do you see how you have these 4 sets of arrows around your periodic table, we're going to talk about what happens as you go down a group and across a period for 4 different types of trends. Okay, that's our goal. The first one is super easy. Okay, it's like, is this even count as a trend? But we'll check this out. The first one we're going to talk about is atomic number. Remind me, what does atomic number tell us? Number of protons. Very good. This tells us the number of protons in the nucleus. So we're going to talk about what happens to atomic number as we go down is this a group or a period? A group. Down a group and across a period. Good. Go ahead and label your first arrow Z for atomic number. And then with the person you're sitting next to, take a look at your periodic table and see what happens to atomic number as you go down a group and as you go across a period. Take like 30 seconds. Ready, set, go. Okay. Can you two chat? Is that all right? Yeah? Actually, let's do a group of 3. Is that good? Okay. Go for it. All by yourself. Can we do a group of 3 here? Is that all right? Like, yeah, no, you're good.
Wait, which arrow did you go?
I'm sorry?
What arrow did you go?
You can choose, but I would just put it on the closest one. We're going to build out. Okay, 5, 4, 3, 2, 1. Okay, to take a look at this, look at your alkaline earth metals. Point to your alkaline earth metals. Boom. All right, now let's go down that group. What happens to atomic number? It goes up, right? We can see that it starts off smaller, and then as we go down that group, it gets larger, right? Which means what's happening to protons? We're increasing. We're getting more protons as we go down. We already knew that, right? We already knew that. And then as we go across, say if we look at period number 5, energy level number 5, and then you look across, easiest trend in the world, what's happening? It starts off smaller, and it gets larger, right? Easy to tell. Okay. So knowing that, if I'm to English, that's wow. Let's try that again. Okay, that's a 3, and that's a 4. Okay, knowing this, in which corner, 1, 2, 3, or 4, do you have the smallest atomic numbers? Number 1, in which ones do you have the largest atomic numbers? Right? Good, so we can look down a group and across a period, but we can also look at the overall trends. That you got your smallest atomic number up there, and your largest one in the corner. Good? Okay, so you see how we're looking at trends. Will you do the same thing with atomic mass in just a moment? Remind me, atomic mass tells us the number of protons and neutrons. These are protons and our neutrons, right? Okay, we're going to see what happens as we go down a group and across a period with our atomic mass, the average atomic mass that you have. Take a second with the person you're sitting next to and identify that trend as you go down a group, across a period. Ready, set, go.
What do you guys think?
Tell us best. I don't know. You got this. Yeah. So our groups are our our vertical lines.
Oh, I thought it meant like the orbital.
Oh, yeah, no. Yep. Good clarification. Yeah. Oh, right? So sometimes I'll put it in parentheses when they haven't done enough experimentation yet to be like 100%, like super confident in it. So that's one of the reasons that they put it in parentheses. Good? Okay, sweet. All right, guys, let's chat about what happens at the very top of a group. Let's take a look at the halogens. Point to the halogens. Where are those found? Boom, right here. Now, if you let your eyes scan down that group, what happens to atomic mass? It gets bigger, right? So it starts off light, because we're talking weight. It starts off light, and as we go down, it becomes heavier, right? Which makes sense. We're adding more protons, we're adding more neutrons. It gets heavier. Then as we go across, right, say, for example, if I'm looking at period number 6. As I look across, it starts off light or heavy? Light, and then it becomes heavier, right? We're gaining more protons and more neutrons. Are there any exceptions to that? Yeah.
The actinoids, all the ones that don't quite have all the ones that have
Right, exactly. The ones with parentheses kind of tend to vary a bit. Awesome. What else? Do you see any specific ones? Like, take a look at nickel, number 28. Take a look at nickel, number 28. If you look before it, we've got cobalt, that is 58.9, and then nickel is 58.6, and then copper is 63.5. What? Okay? Which just tells us that nickel has some lighter isotopes, right? So that's one exception. Are there other exceptions like that? Iron. Let's look at iron, number 26. Okay? And we can see that trend in there. Okay? Any other ones? Oh, come on, there's more. Find them. You got it. Iodine, look at iodine. Okay? We can see that right before it, I've got the beryllium, 127.6, and then iodine's 126.9, and then zedine is 131. So we see again there that there's a little bit of a exception to the trend. Does that mean that the whole trend is wrong? If there are exceptions, is the trend wrong? No, trend is talking about the overall thing, right? It's talking about just what happens overall. So remember that. Even though there's going to be little exceptions, okay, we're focusing on the trends, okay? All right, so far I have taught you nothing new. Let's jump into the new one, atomic radius, okay? Hey, we talked about this last time. Remind me, what is the atomic radius? Yeah, right? So in the very center of my atom, I have what? My nucleus, and then like you just said, on this outside I have my valence electron shell. So the atomic radius measures from the nucleus to the valence electron shell, that very outside part right there. So we're talking a length, we're talking a distance, okay? It's a very tiny distance, but we're looking at this distance. We want to see what happens to atomic radius as we go down a group and across a period. We want to see what happens to that distance between the nucleus and the valence electron shell. Okay? Go ahead and label that arrow AR. Okay? And then flip your periodic table to the back, because that's where we've got atomic radius. And let's look at this one together. Will you guys look at the alkali metals? The alkali metals, which... How do we know where the alkali metals are? Yep, we just labeled them, right? So we see them. What element is at the top of the alkali metals? Hydrogen. So look at hydrogen, and then that first group is called the alkali metals. And then our atomic radius is the number in the bottom of that red corner, right? Let your eyes scan down. Okay. What's happening to our atomic radius? It's increasing. It's increasing. So we can see that as we go down a group, it starts off smaller, and then it gets larger. Okay? Why? Why would that radius get larger as we're going down a group? What's happening at the atomic level? What's happening to the atom? Yeah.
Where the valence electrons are going up the energy level, so instead of being 1s, it's 2s, and so it's bigger.
Right, we're adding on those energy levels. Do you want to expand on that? Same thing. Same wavelength. Look at you guys, right? Every time we go down a group, we are adding another energy level, right? So we're adding these layers on. So that means that it's getting bigger, right? It's a little bit like this. So if I have group 1 here, and then I've got my hydrogen, and then I can go down to the next one, which would be lithium. So that one has 3 protons. And I can see, hey, look, I added another layer. That's going to increase my radius. If I go down to the next one, oops, I always do that. Here we go down to sodium. It's got 11 protons, and I added another layer. That's going to increase that radius even more. Does that make sense? Okay, sweet. So that's what happens as we go down. We're going to increase due to these additional energy levels. As we add energy levels, we're adding layers. Okay. All right, now you guys already knew this. You just didn't know that you knew this necessarily. Does this look familiar? Hopefully it does. This is the graph that you made. Okay? The yellow lines represent our atomic radius. Okay? Where do you see this represented on this graph? How does this show us this? Yeah?
It's the orbital that goes down, that jumps up as
Right here. Right, that jump was where we added the energy level. And then this jump is where we added an energy level. And then this jump is where we added the energy level. Okay? So we saw those massive jumps as you graphed it. Yeah?
what causes the blank space in some table where it just doesn't have anything written for the atomic radius dash?
For the atomic radius?
Yeah, they're.
No, that would be the electronegativity.
So yeah, we have that a couple times for electronegativity. And then if you look in the very bottom left corner, there's a couple of them with the atomic radius. These are elements that are very unstable, and so it's hard to measure, right? For electronegativity, that has a different answer. We're going to talk about that soon, okay? About what's going on there, all right? Okay, good. So we just saw what happened as we go down. It goes from smaller to larger for atomic radius. Let's look and see what happens as we go across a period. Look at period number 4. Yeah, it starts off larger, and then as we go across, it gets smaller. Wait, what? We're adding more electrons, right? We're adding more protons. Why is it getting smaller? Yeah. Yes, you want to say that again louder? Right, guys, well, and it's more about that nucleus, there's more of that positive charge too, right? As we go across, check out what happens. So here we went down the group, right? Now if I show my group 2 and group 3, I can see what happens as I go across. So here, I've got 1 proton. If I look across, I can see I added a second proton, but did I add another layer? No, so more protons means I can pull that outside layer in even closer, right? And then if I look at this next one, and I'm going across, I've got 3 protons here, and then 4 protons, so more protons to pull that in, and 5 protons, which gives me more protons to pull that in closer. So as we, nope. Oh. I've never seen it go black when it died. There we go. Okay, now talk me through this. Here I've got 11 protons, and then when I add 12, what happens?
Electrons get pulled.
It gets pulled in. Those protons are pulling those outer electron shells even closer in. And then here, I added more protons. What's happening? It's pulling it in closer, okay? So as we're going across, that
Does that have to do with like density and stuff?
kind of.
That way, like hydrogen is like so like a gas because, or I don't know how to explain it. So.
Yeah, but so short answer, yes. Short answer, yes. So it works a little bit like this. As we go across, it gets smaller. And then when I come down, I add another layer to it, so it gets bigger again. But then as it moves across, it gets smaller. And then what happens? We add what? More energy levels. We add another layer. And after I add another layer, then as we move across, we're adding more protons that pull those valence electrons in even closer and closer. Okay? Take a second, turn to the person you're sitting next to, and explain it to them as if they were 4. Okay? If you had to explain this to your little sibling to be like, what is happening here? How would you put that into your own words? Okay? Ready, set, go. Okay? You liked that challenge, huh? Nice. I'll go and add that in. You want to give it a shot? That's a really good analogy for that. I like that.
There would be a limit to this where at some point if we were to create extremely large
nuclei, could we make it so that it keeps getting smaller as it adds an energy level because it just stretches them in hard enough?
Oh, that would be really interesting. Theoretically, every time you would add an energy level, you're just adding that probability, the probability of where they're going to be, right? I don't know that I haven't seen if we've predicted far enough to see if that would stop following this trend. I would predict that it would continue to follow the trend. I don't know. Let me check it out. Okay, yeah.
Did you give notes for because you went to like down a group and then across the period, but then there weren't any notes on.
We haven't done that yet.
Okay, cool.
Yeah, you're good. We will get there. We will get there. Okay, guys, if we're looking at your graph, remember the yellow line is our atomic radius. Where is the trend across the period represented? Yeah, right? Right here, as we see this going down, that's across my period, right? That's across my period. That's across my period. And you can see that trend as it goes down, right? So you already saw this trend. You already saw this. And you saw that right here. That's the one you're just asking about, right? As we go across a period, that atomic radius gets smaller because we're getting increased nuclear charge. We're putting more positive charge into that nucleus. Okay, creates more pull. Okay. All right, guys, we throw a star by atomic radius. That one is the big one. If you know atomic radius, you know the others. Okay, you know electronegativity, and then this is the crux of the unit. This is going to help you with everything that's coming forward as well. So we want to know atomic radius, because the last one, electronegativity, directly relies on atomic radius. Okay, electronegativity is an atom's ability to steal electrons. This is how good of a thief they are. How good are they at stealing other electrons? Otherwise known as stealing power. That's the only thing you'll need to write down. That's the stealing power. Okay? Oh, you already been written. Look at that. This depends on shielding. This depends on shielding. Okay? Shielding is interference that's caused by electrons that are surrounding the nucleus. Okay? So now words are helpful, but visuals make a lot more sense. So we're going to label our arrows EN for electronegativity, and then prepare yourselves to see one of the best animations that you've ever seen in your life. Just saying. Pixar might be calling me. Okay? Getting ready. N'importe quoi to make me the head of their company. Yeah, check this out. Ready? Start off strong. Nice, right? There's an electron. Okay, check that out. All right, and boom, I have an atom. Okay, did you notice the dust too? Yeah, thank you. Okay. All right, which atom is this? Hydrogen, right? It's got one proton. It's got to be hydrogen. And then I've got another one. I know, right? It's kind of cool. Okay, this one, which element is this one? Potassium, right? If it's got 19, it's got to be potassium, okay? So now we know that these protons here are attracted to that electron, and this electron is attracted to the protons. So we can see those protons are reaching out, they're like trying to grab that electron, right? And then the electron is like, yeah, sounds good, okay? But tell me about this electron. What is this electron doing? It's pushing it away, right? Negative charge, negative charge. So that electron's like, nope, stay away, trying to repel it, okay? All right, we also have my potassium here. 19 protons. That's a lot of protons. These protons are like, hey, trying to grab that electron. This electron is like, yeah, sounds good. But then we have this whole pile of other electrons. And what are those other electrons doing to this electron in the center? They're repelling it. They're like, nope, stay away. Okay. Now the question is, which element is the electron going to go towards? Is it going to go towards the hydrogen, or is it going to go towards the potassium? Take a second, make a prediction, and then point. What direction do you think it's going to go? You cannot point up. Okay? Is it going to go to the left or the right? Point. What do you think? Have an opinion. Everybody needs an opinion. What direction do you think it's going to go? It's going to we're going to have. That solution. Make a prediction. Where do you think? I'm going to wait till we're all making a prediction. Where do you think it's going to go? Okay, ready for this, guys? This is the best part of the animation. It's going to go to thallium that you didn't even know was there. No, just kidding. It's going to go... Oh, the sparkly star. Okay, those of you who were predicting that would come to hydrogen, why did you think hydrogen? Yeah, right? Remember how this depends on shielding, right? There's less to push back, guys. And here's the thing. What I love about this is that it always follows the same pattern. This relates to the atomic radius. The smaller the atomic radius, the stronger the electronegativity. The most likely it is to steal. Smaller is stronger. That's right. Short people unite. Yes. Because it's got an electron already. So it has one proton, one electron in this case. So this one is neutral already. So if it were to take it, it would take a negative charge, and then it's ready to bond with other things. Okay? But this one, again, the main idea here is that if you've got a smaller atomic radius, you have a stronger electronegativity. It is most likely to steal. Which, guys, we saw that in your graph. Check this out. Every time atomic radius got smaller, what happened to the blue line? What happened to your electronegativity? It went up significantly, right? And then here we can see that radius is getting smaller, and my electronegativity is getting stronger. And then my radius is getting smaller, and my electronegativity is getting stronger. Smaller is stronger. Yes. Yeah.
Since smaller is always stronger, why isn't hydrogen the most electronegative?
Let's check this out. Okay? So here, it starts off, let's predict. Can I answer that question in 2 minutes? Okay, awesome. So here, if it starts off smaller at the top, is this going to be stronger or weaker? It starts off stronger, and then as we go down, it becomes weaker. Okay? It starts off stronger, and then it becomes weaker. And then as we go across a period, I can see that my atomic radius starts off larger, which means my electronegativity is going to be weaker. And then as I move across, it's going to become stronger. So that kind of answers your question here, right? Let's take a look at this. Knowing that, in which corner, 1, 2, 3, or 4, are we going to have the weakest electronegativities? Let's take a look. If I've got weak right here and weak right there, that tells me that my corner number 3 is going to be the weakest. Let's check it. Guys, grab your periodic table. Look at francium down in that bottom left corner, and then our electronegativity is the number up in the top right. Do you see it? What's its electronegativity? 0.7. Is there anything weaker than that? No, it is big and it is weak, okay? Francium is the biggest, weakest element, okay? In what corner are we going to have the strongest, the most electronegative? Yeah, corner number 2, right? That's where we're going to have the strongest ones. Go ahead and look up in corner number 2. Oh, yeah, look at helium. Wait a second. What's with helium? Does it have an electronegativity? No, it has a dash, right? And neon has a dash, and argon has a dash. Okay. I'm sorry?
Where does it show the 0.7 for francium?
So these ones are on the other side.
Oh my god.
You're good? You're good? Okay, so guys, we just have a dash for our electronegativities. Yeah.
Is that because they're noble gases, so they can't react?
Exactly. Guys, those are our noble gases. They can't react. They already have 8 electrons. They have no interest in trying to steal other electrons. Okay? So they don't have an electronegativity. It's not that it's 0, it's that they don't have one. Now then I know that you're going to say, but Miss Call, krypton and xenon have one. And it's like 3. That's kind of a high number, right? So here's the thing. Out in the natural world, those aren't going to react. They don't really have an electronegativity. But in lab, we can hit them really hard and get them to do things. So that's what happened. They hit it really hard and got them to do things. Real hard. Okay? Yes. Like particle colliders hitting them with things. Like literally hit them. Which means when we're looking in corner number 2, you're going to look at fluorine. Look at fluorine. What's its electronegativity? 3.98. Whoa, is there anything stronger than that? Look around that corner. Nope. Fluorine is the strongest, okay? Therefore, it's also the smallest, because smallest is strongest, right? Okay, so guys, if you know these trends, we can then start to make predictions on how they bond together, okay? Will you take your notes and flip it over the back? Yeah. So, that is a good point. When we talk atomic radius, we're talking about their neutral atoms. Yep, yes.
Is Leo both at the bottom smaller or stronger?
Smaller is stronger. Smaller is stronger, yes. Good. Okay, so guys, now that we know this, right, we want to be able to use these trends to make predictions about how they bond together. But the first thing that we've got to do is make sure we understand a little bit more about how the periodic table is organized, all right? On this back of the periodic table, do you see this solid line that's drawn like right there? It's kind of hard to see with my blue. Right here, that line. Okay, we flip your periodic table to the front and draw this line in. It's kind of an important line, okay? Also make sure you draw it in the correct spot. That matters a lot, okay? So it comes to the left of boron, and then it just staircases down, all right? This is our dividing line between our metals and our nonmetals. This staircase line. And it just drops straight down. You'll want to add it in right here. Yes. Yep. Okay. So yeah, this shows us the difference between our metals and our nonmetals. Anything to the left over here, anything on the left is a metal. Okay? And it has properties of metals. We're going to talk about those in a sec. Okay? Anything to the right of this staircase line is a non-metal. Such creative naming in chemistry. Okay? Makes it easy to remember. Metals on the left, non-metals of the right of our staircase line. Okay? So now let's chat about the differences between our metals and our non-metals. Let's look at our left side first. Our metals. Yeah? Hydrogen counts as the left. Hydrogen is a metal. Oh, helium is funky. Helium counts as the right side. Okay? Even though we added it to the left because of its atomic structure, it still counts as the left. It's a noble gas. Good. Yes. Yes. Okay. All right, guys, let's think about our metals. It's on the left side. In general, okay, do they have a lot of valence electrons or a few valence electrons? A few. They generally have a few, right? Most of them only have like 2 valence electrons, okay? And then in general, are they big or small? They're big. They're generally pretty big, right? And if they're big, are they weak or strong? They're weak. Guys, metals are big and they're weak. If they are weak, are they more likely to gain electrons or more likely to lose them? To lose them, right? They're weak, so they're losing electrons, right? If they lose electrons, are they going to take a positive charge or a negative charge? Positive charge, right? Because if you lose electrons, you're losing that negative charge, right? So they're going to become positive. Do you remember what that's called? What type of ion? It's a cation. Good. It's a cation, right? So they form these positive charges. Guys, that's why they do things like conduct electricity, because they're losing electrons. And then they can just be like, electrons go that direction. Electricity, okay? Because of these properties. Nonmetals are different. They're on the right side of that staircase line, okay? Do they have a few electrons or a lot of electrons? A lot. They've got many valence electrons, okay? In general, are they big or small? They're small. And if they're small, are they weak or strong? That's right. They're strong. Okay? If they're strong, are they more likely to gain electrons or to lose electrons? They're more likely to gain them. If they're gaining them, are they going to take a positive charge or a negative charge? A negative charge. And what do we call those? Do you remember? Anions. Nice. They form the anions. Good. They form onions. Yes. Nice. Yes. Okay, and then last are the metalloids. Guys, the metalloids are the ones that are right above and below the staircase. So boron, aluminum, silicon, germanium, just directly above and below. We call them metalloids because they're kind of in the middle of metals and nonmetals. They kind of have properties of both. Okay, which makes things like silicon really nice for computer chips because it's easier to control. It's not just going to shoot electricity straight through. It slows it down a little bit because it's a metal but also a non-metal. It's a metalloid. It's in between. Okay. I'm sorry? Yes, but remember our metalloids right above and below a staircase kind of share properties of both, right? To some degree or another. Okay? Guys, any questions? All right, when I see you in the future, we're going to take these that you know, these are building blocks for then how these all come together and how they bond together. All right? Sweet. Will you... Actually, let me hand out the homework and we're ready to go. Okay? I'm going to stop recording though, and then let's do this.